Dear panel member, myself Jagadish Ramaswami. So it is glad to present my paper in 4th International Conference on Electrical and Electronics Engineering organized by Chittagong University. And my topic of today's session is design and analysis of non-vulnerable pseudo-random binary sequence generation with internal shift and XOR of linear feedback shift register. And my paper ID is 6173. And agenda of the today's session is I'm going to discuss about our abstract of the topic and then followed by introduction and what is the recent advancements that happened in the proposed method that will be discussed in the literature review followed by proposed system and a block diagram, and I'm going to describe the results and discussion obtained in the proposed system. I'm going to conclude the session. Coming to abstract, the linear feedback shift register generates pseudo-random binary sequence, so which is especially used in the 3G wireless standards like code division multiple access wireless communication techniques, and also used in the spectrum technique to avoid interference. Like we have more applications, and the PRBS sequence length becomes vital in this case of LFSR, and it purely depends on the hardware complexity, namely registers. So if I want to increase the sequence length, then I want to increase the registers count. The PRBS generation with internal shift performance along with the XOR on the conventional LFSR was proposed to increase the PRBS sequence length with a minimal hardware complexity. And my results is compared with a conventional technique to reveal the properties of the proposed method. Since it is a pseudo-random binary sequence, it has to be on board with the conventional technique like balance property, run length property, autocorrelation property, etc. And it found that the sequence length was double the same hardware complexity, and also there will be reduced in the switching activity even. So this will reduce the power dissipation of the circuit. Introduction. The linear feedback shift register has numerous applications, as I told, in the field of wireless communication like WCDMA, CDMA, spectrum, etc. And also it has applied in fault coverage, device under test, pattern generation, data compression, etc. And mostly encryption even. And in third generation partnership project, we know it is CDMA plays vital in handling the subscribers, and each subscriber is going to allot a unique sequence code, so that we're going to be generated with the help of LFSR, and the CDMA employs a special sequence as codes, and it's going to reduce the robustness against interferences. And we know that there is always increasing in the demand of network uh, users, subscribers, and we need to provide a minimal interference among them. So there is a need for orthogonal sequences that are going to be generated with LFSR on for spreading the signal over the same bandwidth. And we're going to see the recent improvements carried out to generate the PRBS sequences using LFSR, so that I'm going to propose the next. So linear feedback shift register is a combination of digital logic connected with a sequence of registers with a seed value, and we're going to have a regenerative feedback to the register to generate the sequence of length n. The PRBS have a longer length pattern when we're going to have the seed value, so that's why the seed value becomes a vital. And in this case, maximum length sequence generated will be 2 power n minus 1. And the figure 1 shows the conventional technique LFSR for 4-bit generation. Coming to literature review, so we shown some of the advancements that happen in the LFSR recently. So the first paper is to enhance the security of the multi-bit. So to enhance the security, the multi-bit LFSR technique was proposed. We know that in conventional LFSR, we're going to shift only either a left or right by one shift, single shift. But in this case, we're going to have multi-bit shift. So that what will happen, the security is going to be enhanced. So this multi-bit shift is going to be uh, designed with the help of the additional input. So this input will become the circuit will this input will make the circuit to be have higher complexity. So the complexity is getting increased in the first method. The second one is LFSR reseeding scheme. So we're going to develop a scheme to reduce the power dissipation. So we're going to choose effectively the reseeding value, so that switching transition is going to be reduced. If switching transition is reduced, the power dissipation is also going to be reduced. And next one is the modified output sequence based on swapping the MSB. Most significant bit with 2 cross 1 multiplexer was proposed. So here in this case, consecutives two two consecutive bit of LFSR is taken, and that going to be given to the multiplexer, and it will be checked for whether there is a change or is to be need to be incorporated or not. So that what will happen, it reduce the peak as well as the average power of the conventional LFSR was proposed. And next paper, to generate the PRBS sequence of flexible length vertical stacked LFSR was proposed. So in this scheme, the highest LFSR is stacked over the top, and below which we're going to have a lower number of LFSR. For example, we have 4-bit LFSR. If we're going to take the highest one, the 4-bit, below that we have 3-bit LFSR with 1 bit padded, and below that we have 2-bit LFSR, 1 bit added, 2-bit padded. And finally, we're going to do LFSR. So what will happen? My sequence length is going to be get increase, and it's going to be flexible, so there is not like the formula where 2 power n minus 1. So based on the subscribers length, we can able to generate the flexible PRBS sequence length. And finally, combining internal and external LFSR search, the PRBS sequence length as integrating two sets of LFSR was introduced, and these also generate the PRBS sequence length by combining the internal external LFSR with the minimal hardware little complexity. Based on this, I'm going to propose PRBS generation with internal shift performed along with the XOR on the conventional LFSR to increase the PRBS sequence length with the minimal hardware complexity. So this is the proposed diagram. You can see that on top we have conventional LFSR technique, and we're going to take the conventional LFSR of output as the base for the proposed scheme. Now I'm going to perform the left shift, and I'm going to pad the 0 either in the right bit or in the left bit. If you're going to perform the left shift, I'm going to pad 0 in the right bit. If you're going to perform the right shift, I'm going to pad 0 in the left bit. So then finally I'm going to do XOR operations, and I'm going to find the output. So what will happen in the PRBS output? I'm getting the conventional output as well as the proposed scheme output. For comparison, I'm going to perform the sequence. So this is the algorithm. So PR for the PRBS generation with the left shift of XOR. So we're going to first initialize the seed value for the conventional LFSR techniques, and I'm going to define the parameter like a clock, number of registers, a bit length, and I'm going to evaluate the edge of the clock. So in conventional LFSR, only the edge leading is considered, and I'm going to generate the output. Here, the case of edge leading is going to be considered as well as case of edge trailing is also be considered. So why we are going to consider in this cases, we're going to do XOR operations for conventional techniques as well as shifted versions. So what will happen if I go to do that? So if we're going to do check with the leading trail, then I will get PRBS is equal to NS of I, and while trailing I'm going to get the PRBS of N of new I. So my output will be generated at the trailing edge. So my final PRBS is NS underscore N, and underscore N is nothing but next state new of I. So this is my, so this is the results and discussion. So the first figure shows the number of states versus resistors. So here the proposed scheme is compared with the three existing techniques, like the top is a conventional linear feedback shift register, followed by bit swapped linear feedback shift register, and followed by vertical stacked linear feedback shift registers. So in first one, the proposed scheme is going to be perform similar to the linear feedback shift register and bits after linear feedback shift register, but the vertical stacked linear feedback shift register outperform compared to all other techniques. Why? Because the vertical stacked linear feedback shift register number of state is going to be generators plus one compared to all other schemes, so that the vertical stack perform the outperforms in this first diagram. Whereas in case of second diagram, you can see the number of bits versus sequence length. So number of bits represents the number of flip-flops or number of registers. So if you're going to increase the number of flip-flops or registers, we know that the sequence length is going to be increased, and in a, yeah, and in a LFSR, you can see the number of bits is going to be generated is going to be same, and in bit swapped LFSR is also more or less same. Whereas in vertical stacked LFSR, we know that it is flexible length. So in order to make a comparison, I want to make a equivalent scale, so I have the same level of comparison of method. So it performing the same number of registers, same number of sequence length is shown here. But if you want to increase the hardware complexity, if you're going to increase the registers for the vertical stacked LFSR, then what will happen? Definitely, it will the number of flexible length will be high, but what will happen? The power dissipation, because switching activity will be very more in case of vertical stacked LFSR, as well as the hardware complexity is increasing. So whereas comparatively, our proposed method, how performance in this case, so with the with the options of reduced hardware complexity as well as reduced power dissipation. So this shows the PRBS sequence run length of various positions for the states of conventional method. So here I have considered for 4-bit LFSR. So I have taken the switching activity done in MSB bit, MSB minus 1 bit, LSB bit, and LSB 1 bit plus 1 bit. So here you can see that it all the bits have the same like switching activity, run length property, everything is maintaining the same. So based on this, for the next figure, so in this you can see that the PRBS sequence run length for various positions for the proposed schemes. So in proposed scheme we have taken for LSB value as output as well as MSB value as output. If you're going to consider the LSB value, what will happen? It will the proposed method is performing similar to the conventional techniques. So it's going to have the same run length property, balance property, everything, but switching activity is will be very high in this case. Whereas if you're going for the second case, going to consider the MSB value as my output, then you can see the switching activity is reduced comparatively. So that what will happen, we're going to have more sequence length is also increasing and switching activity also is decreasing. Meanwhile, we are maintaining the same hardware complex. So this is the comparison of conventional techniques with staffed LFSR, vertical staffed LFSR, and proposed method in as a table format. So you can see that the run length of the proposed method is increased compared to all other technique, and also the PRBS sequence length is also twice compared to the LFSR and bit staffed LFSR, also compared to the vertical staffed LFSR. Because in vertical staffed LFSR we are increasing the hardware complexity, but in this case of proposed method with the same hardware complexity we are generating the sequence length of twice or double. So conclusion. So the proposed method we have generated as we have designed the shifted XOR of conventional LFSR was designed, and we have studied the properties of retainment of the proposed scheme. So the method outperforms with the existing method technologies in the PRBS sequence length. Comparison with the bit-stacked LFSR, the switching activity was reduced, which leads to the reduction in power dissipation, and without the multiplexer circuit, because in bit-swapped LFSR we are using the multiplexer circuit. And finally, the PRBS sequence length is doubled in the conventional LFSR with the same level of complexity. So in future, so the method employed will be the proposed method is employed in the spectrum technique. We will analyze the FHSS and DSSS whether performing the same level of error performance as similar to that of the conventional LFSR will be studied, and we're going to check its compatibility. So that is my future. So these are some of the references that we have used here for the proposed work. Thank you.